Hello! As you can see, I've been quite arty with my sticking and my cutting again, and I'm going to try and explain a little bit about the role and importance of the sodium-potassium pump. So this section in the centre here is representing the cell membrane, okay? So outside of the cell, you've got lots and lots of sodium, this Na+, okay? Loads and loads of sodium. On the inside of the cell, you've got lots of potassium, okay? It is negatively charged inside of the cell and positively charged outside of the cell. A little confusing because obviously these potassiums are positively charged, but there are also negatively charged ions on the inside of the cell as well, which make it a lot less positive. So in terms of there being a relationship, a potential there, it's positive outside and negative inside. Okay, so back to the cell membrane then, you've got a sodium channel here, sodium potassium pump in the centre here, and you've got a potassium channel at the end here. It is not always laid out in this fashion. This is just to give you a representation of one of each of these certain areas that are going to be important in this little process. So all along the cell membrane you've got this phospholipid bilayer as well. So you've got a glycerol molecule, which is this little pink spot, and two fatty acids that are facing inwards. Okay, the fatty acids are hydrophobic. They don't like fluid at all, so they attract one another and are sort of pointing inwards. The glycerols don't mind it. They're hydrophilic, so they're going to be on the outside. Okay, so when this particular section of the cell membrane on an axon, for example, receives a positive charge, so say from some sodium that's been released at the synapse, it causes these sodium channels to open up. So let's open some of those up. Here we go. So let's open the sodium channel up, and that allows sodium to then rush into the cell. So let's put some sodium into the cell. Okay. So by putting sodium into the cell now, allowing sodium to leak into the cell, you're increasing the voltage. And these sodium channels along the membrane are voltage gated, so they respond to certain levels of voltage. They respond to high levels of voltage. So the voltage is starting to increase on the inside of the cell. And as I said, these sodium channels are all along the cell membrane. As the voltage increases, more and more of these open and more sodium come in. When the voltage level reaches the threshold, all of these in the cell membrane open all at once, and they open really wide, and they allow loads and loads of sodium to the inside of the cell all of a sudden. Lots and lots of sodium creep inside the cell. So now the voltage on the inside of the cell is absolutely colossal, and that is how an action potential is then created along this axon. All this voltage is just blasting along the axon to the end. When that voltage is at its highest, which is around about 58 millivolts, that's what it's trying to achieve, that high level of voltage allows these potassium channels to open. So the potassium channels now open, and potassium starts to then leak out into the membrane. Okay? So potassium then leaks out outside the cell. And these sodium channels had shut as well when the voltage reached a really high level. So now we've got this the wrong way around. We've now got all the sodium on the inside, and we've got all the potassium on the outside. Well, once the potassium has reached a level, basically it's trying to recreate this equilibrium, you see, because we've got extremely positive on the inside, and it should be negative, and not so positive on the outside. So all this potassium runs outside the cell to try and get that equilibrium. But these channels remain open, so lots and lots more potassium leak out of the cell, and this becomes even more negative. All right, and this is known as the refractory period, where this is way more negative than it usually is. When it reaches its lowest voltage that it's trying to achieve, these potassium channels then close. All right, and now we've got a problem. Both of these channels are now closed, but the potassium is in the wrong place and the sodium's in the wrong place. So we have the use of this sodium potassium pump to recreate the equilibrium, to get the positive charge back outside with the sodium and the negative charge on the inside with the potassium. And the way it works is by the use of this. This is ATP. Okay, so you've got an adenosine molecule and 3 phosphates, adenosine triphosphate, and they're connected up by a ribose molecule here. And what happens is, on this sodium-potassium pump, you've got these little sort of receptor sites here, nice circular ones, which absolutely love sodium. They've got a really high affinity for sodium, so sodium then goes into these little sites. And with the aid of some ATP, which binds to the side of this sodium-potassium pump, it changes the shape of the pump. One of these phosphate groups breaks off and you end up with ADP, but I haven't segregated that for you, so we'll just imagine that one of them has just broken off into there. It changes the shape, so this can now twist into this position. So that's how the sodium then gets back outside the cell. Now that it's out and in this position, these triangular little receptor sites have a really high affinity for potassium. So now the potassium then binds to those sites. And by doing so, it then changes the shape again. And the shape goes back to normal. When the potassium are released back into the cell, the phosphate is then released off the receptor and then can bind back to the ATP, or to make ATP afterwards. And that's really how it works in terms of trying to get the sodium back out of the cell and the potassium back in. And you can see obviously we're removing 3 positives to get back 2, so then there ends up being a negative charge inside and a positive charge outside. And that's how that works.